I was going to present with Bob Grimley, who worked on this project with me, but he wasn't able to get out of Green Bay. I talked to my wife yesterday. She came home from Chicago to 3 feet of snow, so I guess Bob's got a decent excuse. So just a very quick background, Schneider, one of the largest, it used to be the largest privately held trucking company in the country. We went public last year, so I can't say that anymore. I'm going to talk particularly about, you can see we have a number of different service offerings. I'm going to talk about an interesting little problem in port logistics. So this is sort of just old school logistics in contrast to some very interesting talks today. And I hope you will conclude that simple can also be innovative. So this, I've got a confession to make about this picture. This is a bait and switch. This is the Singapore harbor, and actually, I'm not entirely guilty because when Informs put the announcements of the teams on their website, they put this picture on the website, and I saw that and said, boy, I'd like to use that picture. So I contacted Eric, who talked to Mary, who gave me a copy of it. But it gives you an appreciation of the complexity of port operations. I'm going to talk in particular about a problem associated with the chassis that are used to transport containers from the ship, usually to a transloading facility, which can be usually several miles away from the ship. And then there's a cross dock there, and the freight is typically broken out of the containers and put into the standard 53-foot trailers, which will then deliver them to domestic markets. So this is just a little bit of a description of the problem. Ocean containers are put on chassis, brought to a transloading facility, taken to customers. Now, the interesting thing about this problem is that the daily arrival of these containers can vary quite a bit as ships come in, and different customers have freight on different ships. The other thing that is very interesting is some chassis will actually, some containers will be turned around within several hours. So it may come from the ship to the transloading facility and be immediately unloaded. The container empty will go back to the ship and then be placed on the ship. Other times it can be up to 2 weeks, so a customer may decide they're almost going to treat the container as a warehouse, or if freight that's going to be combined into a single trailer comes in from different ships, there may be these delays. So there's an important element to the time which a container lives on the ground on a chassis, which we call dwell time. So there are a couple of decisions to be made. When the business first came to us, they said, we need to know how many chassis we should lease for a whole year versus how many chassis we should use on a daily basis. As we got further into the problem, and you can see here, if I commit to too many leased chassis, they end up being empty for periods of time. If I don't commit to enough of them, I pay the higher cost of the rental chassis. We also found that a little bit counterintuitive, that sometimes, even though there are leased chassis available in the yard to use that you've already committed to, it sometimes makes sense to pass on that leased chassis and go get a rental chassis. And I'll talk a little bit about the conditions that apply there. And it turns out in our models, in our simulation optimization models, 15 to 20% of the time it'll actually be the case that I should not make the greedy decision associated with a chassis. The other thing that came up after we had actually done the initial work with the business, they came back and said, can we use this to do pricing? And we hadn't even thought about that aspect of it, but what we realized was if they're able to use these models to predict what their cost will be associated with this mix of chassis, which is going to give them a competitive advantage over almost all competitors. Just stick with the daily lease, which is what we were doing when this business first started up. So our approach to this, did I miss? Yeah. So our approach to this problem, and this is what I think is the innovative part, each one of these boxes is fairly simple. We started with some data modeling, so we looked at history. In this case, we looked at history, but we could also look at a forecast of the daily demand of chassis, and then built a data profile that described with a parameter perspective that data, and used it to generate hundreds of simulations of scenarios that would have the same characteristics as that either historical or forecast data. We then feed it to an optimization model which basically cheats because it has full look ahead into the future and actually optimizes the solution as though you could see into the future. And that gives us a solution for what the optimal number of lease chassis would be for that characteristic of freight, as well as data points that we can then feed to a machine learning model to train a policy that we can give the business to use on a daily basis to decide when to use either a leased or a rented chassis. So that's the general process. So the data analysis, you can see there's a significant difference in the price point for these two ways to look at chassis. About 2.5 times as expensive on a daily basis, but the shortcoming in the long-term one is you're committed to that chassis for an entire year. So we looked at a year of data and spent time with the business and realized that the nature of freight, which we've known because we've been in the transportation business for so long, is that you get a busy season in the run-up to the holidays. You get a very light season that really starts about Thanksgiving because all the freight has already moved in, and then it drops off and then it picks up again. So we decided to break the year into 3 regimes, and then doing some data modeling, it looked like a truncated normal was the nicest distribution to apply to that. We also found that the day of week distribution was fairly constant across the year, and that a dwell time was best modeled by a discrete distribution, which was also surprisingly independent of the volume. So that's what we used to generate data. And so this is kind of the situation that the business finds itself in each day. I have an available number of chassis, the leased ones that are in my pool. I know how many containers are coming in that are going to need a chassis. I have an estimate of the dwell times for each one of these. And then I know how many containers are coming in today back from the cross-dock facility to release a chassis, which might be a leased chassis or it might be a rented one. So as I said, what we did was we just did a simulation, actually a very simple Monte Carlo simulation, ran it hundreds of times, and for each simulation we ran an optimization model, which is really a quite simple model. I guess the one thing that's interesting in it is, which made it perform so well, is to sort of pre-calculate what I called the order period incidence matrix. So if you look across the top each of that matrix, each row represents an order, and then a 1 indicates that a chassis was engaged by that order during its dwell time. And what we also did to simplify kind of the continuous daily nature of this problem, we actually broke time into what we called half-day periods. So a year consists of 728 half-day periods. And because the idea is a chassis that can be returned in the morning of a certain day can be reused that afternoon. And that seemed to be the cleanest way to handle this notion of the reuse of a chassis in a way that was somewhat similar to the business situation that applied. It turns out that this, we've got about 11,000 orders in a year. The pre-processing and the optimization solves in about 3.5 seconds for every one of the iterations. So in 300 seconds, we're able to run 100 scenarios. This kind of shows you what's going on. So on the top, I have just a distribution of the order arrival process of orders in half-day periods. So you can see there are as many as 80 or 85 in a single day. Other days, no orders arrive. Usually, you'll see a dip on every Sunday because there isn't activity then. But down on the lower graph, you can see what's going on in terms of the use of lease chassis and rental chassis. So the orange line indicates the use of the lease chassis, which you can see hits its ceiling a fair amount of the time, but there's a fair amount of the time where there are a number of lease chassis that are not in use. And you also see that the busiest times of the year are clearly ones in which we have to engage a fair number of rental chassis. And so as you can kind of think about this optimization, if we got some colored pencils out in measured areas, we would see that we're just at the point where I'm balancing the trade-off of an extra lease chassis that'll be unused for a certain period of time with the cost of rental chassis for a corresponding period. So because this was a fairly empirical approach, and I wasn't able to prove any theorems about, I did a couple of things to just get a sense of what the optimization model was actually doing. So on the upper graph are the simulation runs of 100 different simulated optimizations. The data point corresponds to the number of orders that were generated in that simulation. The y-axis corresponds to the optimal size of the lease pool that was selected. And then the actual data is that orange point, if you can see about the third of the way out. And so we found that, as you might expect, there's a high correlation between the number of orders that are generated and the optimal number of leased chassis. I also, to kind of understand the sensitivity, I took an example of an optimal solution, and I said, okay, I've got the optimal solution, but I'm going to force my lease chassis size to move away from that optimal, but I'm still going to solve the optimization problem with the rest of the criteria. And you can see that it's hard to tell the scale there, but a movement in about 1% of the cost corresponds to a movement of about 10 units of capacity. So it stays fairly flat in there. And this is sort of, I guess you would say, empirical justification that this kind of a simulation approach actually gives the business a robust solution to this kind of a problem. So, as I said, once I've solved this problem, not only do I have the optimal number of chassis, or at least in some sort of a stochastic optimization sense, I also have data points corresponding to every order because I know whether or not the optimal solution picked a leased chassis or a rented chassis, and I also know the attributes associated with that order that are going to be the attributes that I can actually see in the field that don't have the cheat of looking all the way into the future. So as I mentioned, I think I mentioned these same criteria before, that we then trained a logistic model. So here's a little bit of standard R code, and we got surprisingly good results in terms of how the model trained. We use a Hosmer-Lemschau test to compare along different probabilities to see that there was a fairly good fit. And then we took the, so we had each of, in this case we took each of 10 different simulation runs, and applied the business rule to that and looked at how similar the results of a certain kind of attribute were across those data sets. And our standard error was in the 4% range. So again, fairly strong evidence that this approach, while empirical, seems to hold together kind of all the way through the process. And what we actually ended up implementing was a little bit of a variation on the business rule. So the logistic regression gives us a probability, but we also have the fact that if I run out of leased chassis on a given day, it doesn't matter what the probability is associated with the next order that comes in that day. It's got to take a rental chassis because there aren't any leased ones left. So what we do is we take the orders that we know are coming in this day, calculate their probabilities, sort them by descending probability, and accept and put them on a lease chassis until either we get to 0.5 or we run out of chassis. Now lately we've done a little bit of playing with whether or not 0.5 is the right number, but that's essentially the concept. And then I was thinking about where else could you apply this particular approach. When I did a literature search, I surprisingly didn't find examples of taking this approach of Monte Carlo simulations and feeding them to an optimizer this way. Almost everything I've seen in optimization simulation combination seems to go the other way. So basically the key components of this to allow you to extend it to another area are that I have assets that essentially perform the same task with a different cost and commitment profile. I need representative data to build these arrival processes to do the simulation, and then I can't have preemption or swapping because I can't take back something and put it on the lease chassis if I've already put it on a rental chassis. And some examples of this, the first thing that occurred to me was not too long ago, I needed a car for a trip to Chicago, and the company has a fleet of cars, but if they're all checked out, I got to go over to the airport and get a rental car at a higher cost. And it seemed to me that we haven't actually implemented that because we only have like 20 company cars, but for a bigger organization, that would be an example. I was talking to one of the consulting firms and described this to them, and they mentioned the idea of committing to a block of hotel rooms. If you're a consulting company, maybe KPMG and Marriott, you're going to say 6 months or so, I'm going to commit to this many rooms, similar to one of the places that discounts hotels. But again, the idea of making a commitment with a cost differential seems to be an application. I think there are also some potential applications if you think about either dedicated or flexible machines that have different setup costs and commitments to a certain workload, as well as contract manufacturing. So I do think that there are applications of this same phenomenon that would be interesting. And I think that's it. Thank you.